Xenon difluoride is a powerful fluorinating agent with the chemical formula xenon difluoride, and one of the most stable xenon compounds. Like most covalent inorganic fluorides, it is moisture sensitive. It decomposes on contact with light or water vapor. Xenon difluoride is a dense, white crystalline solid. It has a nauseating odor and low vapor pressure. Structure. Xenon difluoride is a linear molecule with an ZF bond length of 197.73 plus or minus 1215 pm in the vapor stage, and 200 pm in the solid phase. The packing arrangement in solid xenon difluoride shows that the fluorine atoms of neighboring molecules avoid the equatorial region of each xenon difluoride molecule. This agrees with the prediction of VSEPR theory, which predicts that there are 3 pairs of non-bonding electrons around the equatorial region of the xenon atom. At high pressures, novel, non-molecular forms of xenon difluoride can be obtained. Under a pressure of approximately 50 gigapascals, xenon difluoride transforms into a semiconductor consisting of xenon tetrafluoride units linked in a two-dimensional structure, like graphite. At even higher pressures, above 70 gigapascals, it becomes metallic, forming a three-dimensional structure containing xenon octafluoride units. However, a recent theoretical study has cast doubt on these experimental results. Chemistry. Synthesis. Synthesis proceeds by the simple reaction Z plus F2 xenon difluoride. The reaction needs heat, irradiation, or an electrical discharge. The product is a solid. It is purified by fractional distillation or selective condensation using a vacuum line. The first published report of xenon difluoride was in October 1962 by Chernik, et al. However, though published later, xenon difluoride was probably first created by Rudolf Hoppe at the University of Munster, Germany, in early 1962, by reacting fluorine and xenon gas mixtures in an electrical discharge. Shortly after these reports, Weeks, Cherwick, and Matheson of Argonne National Laboratory reported the synthesis of xenon difluoride using an all-nickel system with transparent alumina windows, in which equal parts Z and F2 gases react at low pressure upon irradiation by an ultraviolet source to give xenon difluoride. Williamson reported that the reaction works equally well at atmospheric pressure in a dry Pyrex glass bulb using sunlight as a source. It was noted that the synthesis worked even on cloudy days. In the previous syntheses, the F2 reactant had been purified to remove HF. Smalk and Lutar found that if this step is skipped, the reaction rate proceeds at 4 times the original rate. In 1965, it was also synthesized by reacting xenon gas with dioxygen difluoride. Solubility. Xenon difluoride is soluble in solvents such as bromine pentafluoride, bromine trifluoride, IF5, anhydrous HF, and CH3CN, without reduction or oxidation. Solubility in HF is high, at 167 grams per 100 grams HF at 29.95 degrees Celsius. Derived xenon compounds. Other xenon compounds may be derived from xenon difluoride. The unstable organoxenon compound Z, CF3, can be made by irradiating hexafluoroethane to generate CF3 radicals and passing the gas over xenon difluoride. The resulting waxy white solid decomposes completely within 4 hours at room temperature. The XEF plus cation is formed by combining xenon difluoride with a strong fluoride acceptor, such as an excess of liquid antimony pentafluoride, antimony 5-fluoride, xenon difluoride plus antimony 5-fluoride XEF plus SBF-6. Adding xenon gas to this pale yellow solution at a pressure of 2 to 3 atmospheres produces a green solution containing the paramagnetic Z+2 ion, which contains a Z-Z bond. APF denotes solution in liquid antimony 5-fluoride. 3Z, G, plus XEF, plus APF, plus antimony 5-fluoride, L, 2Z plus 2, APF, plus SBF minus 6, APF. This reaction is reversible. Removing xenon gas from the solution causes the Z plus 2 ion to revert to xenon gas and XEF plus, and the color of the solution returns to a pale yellow. In the presence of liquid HF, dark green crystals can be precipitated from the green solution at -30 degrees Celsius. Z plus 2 APF plus 4 SBF minus 6 APF Z plus 2 minus 21 S plus 3 F minus APF. X-ray crystallography indicates that the ZZ bond length in this compound is 309 pm, indicating a very weak bond. The Z plus 2 ion is isoelectronic with the I minus 2 ion, which is also dark green. Coordination chemistry. Bonding in the xenon difluoride molecule is adequately described by the 3-center 4-electron bond model. Xenon difluoride can act as a ligand in coordination complexes of metals. For example, in HF solution Mg ASF6 2 plus 4 xenon difluoride Mg xenon difluoride 4 ASF6 2 crystallographic analysis shows that the magnesium atom is coordinated to 6 fluorine atoms. 4 of the fluorines are attributed to the 4 xenon difluoride ligands while the other 2 are a pair of cis ASF-6 ligands. A similar reaction is Mg ASF6 2 plus 2 xenon difluoride Mg xenon difluoride 2 ASF6 2. In the crystal structure of this product, the magnesium atom is octahedrally coordinated and the xenon difluoride ligands are axial while the ASF-6 ligands are equatorial. Many such reactions with products of the form Mx xenon difluoride N AF6X have been observed, where M can be Ca senior, Ba, Pb, Ag, La, or Nd and A can be as Sb or P. Recently, a compound was synthesized where a metal atom was coordinated solely by xenon difluoride fluorine atoms 2Ca ASF6 2 plus 9 xenon difluoride Ca2 xenon difluoride 9 ASF6 4. This reaction requires a large excess of xenon difluoride. The structure of the salt is such that half of the Ca2 plus ions are coordinated by fluorine atoms from xenon difluoride, while the other Ca2 plus ions are coordinated by both xenon difluoride and ASF-6. Applications. As a fluorinating agent, xenon difluoride is a strong fluorinating and oxidizing agent. With fluoride ion acceptors, it forms XeF plus and D-xenon monofluoride plus 3 species which are even more powerful fluorinators. Among the fluorination reactions that xenon difluoride undergoes are oxidative fluorination, pH3TeF plus xenon difluoride pH3TeF 3 plus xeroductive fluorination, 2-Cro2F 2 plus xenon difluoride 2-Crof 3 plus Z plus O2 aromatic fluorination, alkene fluorination, radical fluorination in radical decarboxylative fluorination reactions, in Huntsdecker-type reactions where xenon difluoride is used to generate the radical intermediate as well as the fluorine transfer source, and in generating aryl radicals from aryl silanes. Xenon difluoride is selective about which atom it fluorinates, making it a useful reagent for fluorinating heteroatoms without touching other substituents in organic compounds. For example, it fluorinates the arsenic atom in trimethylurene, but leaves the methyl groups untouched. CH3 3As plus xenon difluoride, CH3 3ASF2 plus Zex2 can similarly be used to prepare N-fluoroammonium salts, useful as fluorine transfer reagents in organic synthesis, e.g., SelectFluor, from the corresponding tertiary amine. Rn plus CH2CH2 3N BF4- plus xenon difluoride plus NaBF4 Rn plus CH2CH2 3N plus F BF4- 2 plus NaF plus Zex2 will also oxidatively decarboxylate carboxylic acids to the corresponding fluoroalkanes. RCOOH plus xenon difluoride Rf plus CO2 plus Z plus HF silicon tetrafluoride has been found to act as a catalyst in fluorination by xenon difluoride. As an etchant, xenon difluoride is also used as an isotropic gaseous etchant for silicon, particularly in the production of microelectromechanical systems, MEMS, as first demonstrated in 1995. Commercial systems use pulse etching with an expansion chamber. Brazel, Dokmasi, et al. Describe this process. The mechanism of the etch is as follows. First, the xenon difluoride adsorbs and dissociates to xenon Z and fluorine F on the surface of silicon. Fluorine is the main etchant in the silicon etching process. The reaction describing the silicon with xenon difluoride is 2-xenon difluoride plus C2Z plus silicon fluoride. Xenon difluoride has a relatively high etch rate and does not require ion bombardment or external energy sources in order to etch silicon. References. Further reading. Greenwood, Norman Neal, Earnshaw, Alan 1997. Chemistry of the Elements, 2nd ed. Butterworth-Heinemann. p. 894. ISBN 0-7506-3365-4. External links. Webbook page for xenon difluoride.